Servus, guten Abend, guten Tag, herzlich willkommen, and welcome to the 11th and final installment in the plenary series of the SSC. Before getting started, we want to thank our supporters. We couldn't have done this without them: Matrix, OstMS, AMSI, and UNSW Sydney. Reminder to ask questions using the Q&A feature down below. Our speaker today is Eva-Maria Hainzl, a second-year PhD candidate supervised by Michel Drmota. Eva's work is mainly in analytic combinatorics, but she also enjoys problems with a geometric and number theoretic flavor. Eva did her bachelor's and master's studies in discrete mathematics at TU Graz, including a year at Charles University Prague as an Erasmus student. Even before this talk, Eva has made invaluable contributions to the symposium. I was honored to have her in attendance at my presentation, in spite of the age-old wisdom that one does not, under any circumstances, attend an organizer's talk. Nevertheless, she noticed my desperate need for help with my figures and suggested Eip to me. I've already used it to draw some lovely figures, so I'm very grateful for the suggestion. I should also mention that Eva has a degree in stage and costume design at the Graz University for Music and Performing Arts. This is fortunate, as Eva was present at our social event, Would I Lie to You, where it came to light that there exists, in some form or another, a musical about the life of the great Évariste Galois. So, if the lasting legacy of this symposium is that one day a sellout performance at the Burgtheater, I think we can consider that a win. Today, Eva will be teaching us about geometric domination, also known as revenge of the pawns. Please join me in welcoming Eva, and over to you.
Oh, thanks, Jack, for the nice introduction. About this Galois musical, I actually know some very musical mathematicians here in Vienna. So if there's scores, please send them to us. We will get back to you with a video where we brought this musical on stage. Okay, and really thanks for this whole week. It was such a nice conference. It was really well organized. I was so surprised. That even after 2 years of COVID, where everyone is really just fed up with these online events, that you managed to make such a nice event where you really feel like, oh yeah, I want to go there. I want to see Would I Lie to You. I want to see this panel discussion. I actually want to watch this video from the talk during the night and whatever. So I think you made very good choices and really very, very well organized. So congratulations, and really thank you for inviting me. It's a pleasure. Okay, I'm gonna share my screen now. And we're going to my problem, geometric dominating sets. So like Jack said, I actually do a PhD in analytic combinatorics, which is mostly concerned with generating functions that have a positive radius of convergence. So they basically just Taylor expansions of analytic functions. And you use mostly tools from complex analysis to study discrete objects, which is a super cool thing to do and a very powerful method and whatever. But for this talk, I really decided to talk about a topic that I actually already worked on as an undergraduate student or like as a master's student. Because for me, it's really everything that there is to love about combinatorics. It's a very simple, easy to understand question that you can like tell anyone. You can go to your mom, who's like a nurse like mine, and explain to her, well, this is the problem. Let's try to solve something. Let's try to get some result. And everybody would understand how it works. And at some point you realize, whoa, this is hard. Why is it so hard? And how can I find a way to get a hold on this problem? How can I, what model can I abstractly use to try to understand the problem and whatever? But apart from that, it's just really playful. It's very open. There's no techniques or something that are sort of needed to understand the problem, to work with the problem. And there's lots of open questions. And I hope after this talk, maybe when you're sitting together with your friends and take out a chessboard or something, like you come back to this problem and say, okay, let's play. Maybe we can improve something or something like this. So it's really about the fun in combinatorics, I think. Okay, so we start off with like a very classic fun problem on the chessboard. It's the queen's domination problem. And it asks for the minimum number of queens to dominate the chessboard. And if you've never played chess, queens are very powerful pieces on the chessboard. They can basically move horizontally, vertically, and along diagonals. So all on the, like this queen here can move to all of the green vertices. And where the queen can move, the square is dominated. So on the chessboard, all the squares that I marked here red are dominated by this one queen. And if we add 4 other queens here, for example, then the whole board is dominated. You can check this. And well, on an 8x8 chessboard, you can do a bit of trial and error for a few hours or something and find out, okay, 5 queens is actually the minimum number that we need to dominate the board. And well, this is one possible configuration, that there's actually loads of other configurations that will dominate the board. But as we are mathematicians, we would think of, okay, what if we have an n times n chessboard? What are we going to do now? And what people did in like the 1950s, they created the so-called Queen's graph. So going back, so every square now is a vertex in our graph, and 2 vertices are connected in the graph if a queen can move from this square to this square. And they looked at it as the Queen's graph, and then they were looking for the domination number of the Queen's graph. And if you've ever had a course on graph theory and heard about domination numbers, this is not a coincidence. It's not like people in maths came up with the domination number in graphs first, and then people realized, oh yeah, maybe we can solve this cute chess puzzle or something. This was really like people were looking at this fun problem and realized, okay, this is like a problem that has like real importance in graph theory. Maybe, yes, it does. And this really fed each other. So this the study of domination numbers in graphs became a whole new momentum with this domination number in the Queen's graph. And of course, we could also ask for constellations of queens where no queen is allowed to attack another queen. So here, for example, the queens are at distances where they're not dominated by another queen. And this would be an independent set, an independent domination dominating set in the Queen's graph. So here we have the independent domination number, IN. So this problem is super hard. It's proven to be NP hard. We actually do not know the correct number for, finding the domination number in a general graph is NP hard. This is a specific problem in the Queen's graph, but even there we do not know the exact number, we just know bounds. So easy problem, hard to understand, hard answer, still open actually. So, and people are still sometimes publishing papers about this problem. And what people also studied, apart from this Queen's graph, they also studied the Rook's graph, they studied the Knight's graph, they studied the Bishop's graph, they even studied the King's graphs, even though kings are really, okay, I'm not a chess player, but in my opinion, in 90% of all cases, you only need the king to lose. So I don't know why people are actually interested in this piece. But what people never studied is pawns. Like this might be because pawns somehow have a direction. So you wouldn't have like a normal graph, you would have more like a edge-colored digraph or something like this. But nobody seemed to be interested in pawns because they're weak and weird somehow. So we decided to give these pawns like a special superpower. We said, okay, if we have 2 pawns, then these 2 pawns, they define a line on the board. And all the squares that are on the line of these that are on the line that the 2 pawns define, they're dominated by the 2 pawns. So here it's also easier to go to this more abstract setting where we have this grid and we just say, okay, here's a pawn, here's a pawn. Then in the plane, they define a straight line, and this line intersects with this point and this point. So these 2 squares are dominated. We add a 3rd pawn up here, then the whole column is dominated, and these 2 points would dominate this square here in the left corner down there. Right? So that's the domination set situation here with the 3 pawns. And now, very naturally, we would ask for the minimum number of pawns that we need to place on an n times n chessboard to dominate the whole board. And really notice here that now this is a problem that we cannot really grasp as a graph theoretic problem anymore. because we need 2 pawns, and what would be our vertices then, and what would be the dominating set or something. So it's slightly different, and we give it a new notion. We call it the geometric dominating set problem. And the minimum number of pawns needed then is the geometric domination number that we denote by dn. And then, of course, again, we can ask for a set where no 2 pawns are allowed to dominate another pawn. So no collinear triples allowed in our dominating set. How many pawns do we need at least to place on the board to dominate it if we do not allow these collinear triples? And this would be our independent geometric domination number, in. And just because we're now clear that we're talking about geometric domination, I will probably only refer to the independent domination number and the normal domination number of the board and leave out the geometric. But just be aware that this is a very different notion of domination in that sense. So the second variant, the minimum, we do not allow collinear triples. This is actually connected to another famous problem in discrete geometry, the no3 inline problem, that asks for the maximum number of pawns. Sorry, that asks for the maximum number of pawns that we could place on an n times n chessboard without creating a collinear triple. And here, this is a sort of a min-max version of a set without collinear triples, right? And this problem actually already appeared in the literature in the 70s in Martin Gardner's mathematical games column. So it's also in a fun topic somehow, but there were mathematicians that tried to obtain results on that. And it seems to be a very hard problem because there's no real advances. There's only results if you restrict lines to diagonal, straight and horizontal lines. But this is a problem that is actually also quite relevant. Like my collaborators, David Eppstein and Oswin Aichholzer, met in 2018 at the Baller's Winter Workshop on Computational Geometry. And they were interested in point sets without collinear triples, because in computational geometry, very often you want in your n times n grid, you want sets without collinear triples. And there's a threshold that is actually sublinear. So if you choose a random set of size that is larger than this threshold, then it's actually very, very likely that you have a collinear triple. But let's say you want to draw a straight edge graph or something on a linear number of vertices in your n times n grid, then it's very likely that you have a collinear triple, and then you wouldn't see a straight edge between 2 vertices that have a third vertex in the middle or something. So for computational geometry, it's an interesting question to generate these sets without collinear triples. And this minimum version never received any results. So this was also a reason why we started to investigate this question. Right, so I already hinted that this is not a particularly easy problem. Just like the Queen's domination problem, we do not expect that I can give you like a definitive result. So something like, okay, it's 1/2 n or something. But I can give you some ideas how you might want to think about the problem and what bounds we can achieve on our chessboard. And maybe you have some ideas or whatever and can improve some things. Okay, let's move to lower bounds. So what will we do for a lower bound? Let's just assume we already have a dominating set. We might not know what it looks like, but let's assume we have a minimal dominating set. And then we could say, okay, yeah, so 2 pawns from the dominating set, they definitely define a line. At worst, every pair defines a distinct line. And each line on our board will dominate at most endpoints, of course. There's no way that it could dominate more. So this expression here on the left of this inequality is an upper bound on points that our set would dominate. And if it's a dominating set of the whole board, then this number has to be at least n squared. So if you do the math, then you will quickly realize, okay, dn has to be bounded from below by some constant times square root n. But what you will also see already in this picture is that not all lines dominate endpoints. In fact, there's only 4 lines that dominate endpoints. The diagonals at most 4 points. If you move this point, if you consider this point, then the diagonals do not even dominate endpoints. So there's at most 4 lines that dominate endpoints. There's at most 4 lines that dominate n-half points. There's at most 8 lines that dominate n-third points, and so on. So basically, we could do refined counting and find maybe a better bound. And if you do this refined counting, you really need to understand how these lines work. How many lines are there that dominate n over a points, basically? And this brings us to a topic that is actually well studied in number theory, visible points. So a visible point from the origin here, the blue point, is a point where if you draw to the line to the point, it does not intersect with any other points. So here the orange points would be visible points in this column here. And we only consider this gray area because we can, by symmetry, we just multiply by 2, whatever. So we're only interested in this gray area here. And we're looking at these visible points. So this is somehow a geometric definition of 2 points being co-prime, right? If they would have a common divisor, then there would be a point where the line would intersect. Okay, so this is how we can uniquely identify these lines by their visible points. And then we also realize how many points are there, where we have a visible point in the 8th column. And this would be phi of a, where phi is the Euler phi function. So this is literally just the number of values that are co-prime to a and smaller than a. So exactly the number of visible points here in this gray area in the 8th column. And you also see, well, if this segment does not intersect any points, then this segment won't intersect any points, and this segment won't intersect any points or whatever. So this line here defined by a visible point that has a as x coordinate will dominate roughly n over a points. Technically, we need to take the floor function here because the board could be smaller, but that's pretty much it. So this is if you're at this point that you understand how many lines are there that dominate n over a points, then you can do a similar calculation and actually derive that the lower bound for dn is rather n to the 2/3 than n 1/2. Okay, so this is definitely a non-trivial lower bound that I think you couldn't improve by a counting argument. So if you would like to improve that, I think there you would need more insight or more ideas or more techniques or something like this. But by counting, I don't think you can do better than 2 to the 2/3. And of course, every independent dominating set is a dominating set. So also the independent domination number is bounded from below by this number. Question here is just whether this is a strict inequality. In general, we do not really know. We know, for example, that I7 is 8 and D7 is 7. So in general, it's not the same number. But for example, for n is 8, the two numbers coincide again. So technically, it's possible that, let's say, every n which equals 0 modulo 4 or something, the two numbers coincide because of, I don't know, some symmetries or whatever. But for all the other numbers, there's a strict inequality or something like that. So we do not know about this. Yeah, so these are questions for the lower bounds, definitely. Let's maybe have a look at upper bounds and how small we can make the window. And for the upper bound, we will do like a small experiment. So we start with our chessboard. We start with the usual chess setup. We have 2 lines of pawns. And now we try to remove as many pawns as possible and see with how many pawns we are left and see how this works. And as soon as you try to start to do that, you will realize we can't remove any points from this setting. No way. And the reason is, again, very simple elementary number theory. On an 8x8 chessboard, these 2 lines are a distance 5. And we've already seen this visibility argument from the points. So if we take 2 points that do not 2 pawns that do not define a diagonal or a vertical line, then the segment between those 2 points will not intersect with any other points here because 5 is a prime number. So the only lines that in this setup are relevant are vertical lines and diagonal lines. And if you look at the diagonal lines, well, they do dominate a lot of points, but the blue points here, they are only dominated by vertical lines. and there's a blue point in every column. So as soon as we remove a pawn, this point will be free. So we can't remove anything. But now we got a bit smarter, and we might think, okay, what if we move the two lines together? And now they're at distance 1. So now we shouldn't have this problem anymore, right? Now 1 will give us like nice slopes of any kind. In this case, it is true. Now we can remove a lot of pawns. We can actually halve the number of pawns that we need here to dominate the board. And this is really just because now we have vertical horizontal lines, we have diagonal lines, but now we also have lines with slope 1/2. And this construction works for every board size. And it's literally the best construction that we have right now for our upper bound. So this gives us an upper bound of n if n is even, and n+1 if n is odd. But this construction is also only tied up to n is 6, and it's tied for n is 8. But for n larger than 8, this construction is definitely not optimal. So if you can find any other construction for larger boards, this is like real improvement. And at this point, I mean, there's not much theory going on there. So maybe you have some ideas from some other field or whatever. Oh, we can create a dominating set by doing this and that or whatever. So I think there's still room for input from all sides. Yeah, let's also have some look at numbers for the independent domination number, because the independent domination number is very closely connected to this Noetherian line problem that has been open for more than 100 years now. So it's very hard, and we actually have no idea how to obtain an upper bound there that is not trivial. And obviously an obvious trivial upper bound would be 2n, otherwise by the pigeonhole principle you would have 3 pawns in 1 column or something like this. So we only have computational results, and we also only have computational results for n up to 12, right? So because even obtaining this number here, it took weeks. So there's also room for improvement, I would say. But let's have a look at the numbers. So the independent domination number here, up to 8, we already know, okay, I8 is 8, I7 is 8. We've already seen this picture on the previous slide. But for n larger than 8, we can see, okay, IN is definitely smaller than n. And what's also interesting is that, so in this line here, we see the number of different configurations that give us this optimal IN. And here for n is 10, there's really only one distinct solution up, so modulo symmetries and rotation and whatever. So if you rotate it, you get 4 different solutions. But there's really only one single solution that would give us this number here. And for 12, there's only 2 distinct configurations that would give us the independent domination number of 10. And if you look at these configurations, it's not like they're subsets of, that there's a configuration, for example, for 7 that would be a subset of the optimal configuration of 12 or something like this. So it's really like every n has a unique fingerprint that would give you this optimal number. And it's not quite clear how to generalize this or how to derive general construction from these computations. If you want to go higher with your n, you need to come up with something better. And like whenever I'm stuck, I just try to be fun. So we're going to play a game, basically. We're going to play a game. You play a pawn, I play a pawn, you play a pawn, I play a pawn. And the first one that creates a collinear triple loses. And then we just see how many pawns we can place, basically. So you play this white one here, I play the black one, I play the white one, you play the white one, I play a black one. And at this point, you probably realize that I kind of set you up, right? Because I let you do all the work. You look for a square that is still free and you put your pawn there. And I just, I'm like, okay, maybe I mirror. And by symmetry, this square has to be free, and I can put my pawn there. So if the board is even like a normal chessboard, then I will always win and you will do all the work, which is like really nice. And you can do this with different board sizes, but at some point your friends will not want to play with you anymore. They might want to play with you on odd boards because we do not know whether there's winning strategies for odd boards. But yeah, for larger boards, at some point you just have to write a computer program to play with you, and then you can obtain some better bounds for n larger than 12. And of course, like these configurations that you get there, they have some symmetry, so they're definitely, or they're probably not optimal, but they're definitely upper bounds for the independent domination number. And here we can see all these upper bounds are well below n. And the best ratio is actually here the solution that we have for n21, which gives us something like 0.762. So about 3/4 n. And in that sense, it's very reasonable to assume that there is a constant such that the independent domination number is bounded from above by 2 minus constant times n, right? If n is large enough. But at this point, we really don't know. We cannot even prove that there's an independent dominating set of size 2n minus 1, which seems ridiculous, but really we've talked with lots of people about this. There's really a lot of people who thought about this, and it's not easy. But sometimes you're just lucky. Sometimes you have a great idea, or you have a great technique up your sleeve and you didn't know that, oh, I can use it for something. This might be the problem where you can make some progress. Cool. Another idea about this upper bound is also given by the Noetherian line problem that I already mentioned. This Noetherian line problem again asks for the maximum number of pawns, or I already talk a lot about points in grids. So let's smoothly move to points in grids. So it asks for the maximum number of points in an n times n grid such that we do not have collinear triples. And there is, I've already said it's open. It's been open for more than 100 years. We do not know whether we can achieve 2n in general. We know that we can achieve 2n up to, I think n is 48 or something like this, n is 50 or something. But it's actually generally believed that it's not possible because of a conjecture that was published in the late 60s by Richard Guy and Patrick Kelly. And they computed some heuristics where they found out that the upper bound, like the maximum number of points for large n, should be around pi over square root 3 times n, where pi over square root 3 is about 1.8 something. And actually in the initial computation, there was some computational mistake, and this computation was corrected by Gabor Ellman in 2004. Indeed. And yeah, when I read this paper, or when I found this paper, I was really excited because as an Erasmus student in Prague, I sneaked into a Combinatorics conference and I heard a talk about random graphs and logic by Mark Noy, and I immediately fell in love with probabilistic combinatorics. And I thought, oh yeah, this is the thing. I should go into that. And yeah, so let's have a look at their heuristics, because right now for us it's a very classic heuristic, I would say, that one could easily compute. But back then in the 60s, where the probabilistic method was very new, this was like a real thing, I would say. So what they do is they say, okay, we take our n times n square, n times n grid, and we choose a point set S uniformly at random from this set. And the point set S is of size kn, where k at this point is not determined yet. Usually with these probabilistic arguments, very often you take k as some sort of number that you want to that you actually fix at the very end of your reasoning somehow, because then something converges to 0 or converges to 1 or something like this. So we choose a point set S of size kn uniformly at random from our grid. And then we compute the probability that 3 random points are collinear. We can do this with our understanding of the visible points in an n times n grid, actually. And this probability is about log n over n squared times the constant. And then once we know this, they say, okay, let's assume that 3 points are collinear. This event that 3 points are collinear are independent. And then the probability that S contains no collinear triples is just the product of the individual probabilities. So this would be 1 minus p to the number of triples that we can choose from our set S of size Kn. And well, if you use some asymptotics, then you will find out, okay, the asymptotics of this probability is n to the minus k to the 3 times n times some constant. So this is the assumption. And then you say, okay, we chose set uniformly at random. So if you remember, uniform distribution is just the number of good events divided by the number of all events. So if we multiply this probability here with the number of all events, that is, if we multiply it with the number of ways how to choose a set of size Kn from our grid, then we should get the number of good events, the number of point sets without collinear triples, right? So then we use again some asymptotics, and you can see, well, if k is now larger than pi over square root 3, this thing will converge to 0. So for n large, this number will be smaller than 1, so there will be no set without collinear triples. The only thing now is that we assumed that the events that 3 points are collinear are independent, which they are of course not. It's just a heuristic. If we consider like 4 points and x1, x2, x3 are collinear and x2, x3, x4 are collinear, then of course we already know that x1, x3, x4 are collinear. This event is fully determined, yeah, then. So there's actually a lot of dependence going on. And the heuristic is really just a heuristic. And when I read this paper, I thought, okay, but this really reminds me of like a classic outline that you would use in random graph theory when you want to do computations on events that are dependent, because sometimes the dependence is very small and asymptotically it doesn't really matter. But this dependence is hard to grasp in these uniform distributed subsets. So actually we will use another model, and this is what I'm going to introduce now. And I first give you like a small idea about random graphs, and then you will see, okay, this is basically the same as random hypergraphs, random subsets, whatever. So the classic two models in random graph theory is basically the uniform random graph, where, well, we fix the number of vertices, n, and we fix the number of edges that we want in our random graph, which is just m, and then we choose the graph with m edges uniformly at random from all graphs with m edges on n vertices. Well, that's it. And then we have a second model that is called the binomial random graph, where we also fix the number of vertices, n, but we have a probability p that says, if we go through the edges, we ask each edge individually, are you in our graph or not? So we ask, are you in our graph? And with probability p, it says, yes, I'm in your graph. And with probability 1 minus p, it says, no, I'm not. And we do this for all our edges, and we end up with a graph in the end that might not have m edges. But if we choose p such that p equals m over n choose 2, then we expect this graph to have m edges. And then we would also, like, just as an intuition, we would also expect to that this graph somehow behaves similarly to this uniform random graph, right? So when we create these random graphs, it's really, we're choosing random subsets of a given set that we call the edge set. So very naturally, you can just generalize this and say, okay, we can do the absolute same thing with subsets of our integer grid, for example. Or you could also, like, we've already seen a lot of talks on hypergraphs. Same thing here. Same models in principle. So we have our uniform random point set subset that we can choose, that we will denote by r and n, where n is like the size of our grid, n times n, and m is the number of points that we choose in our uniform random set. And here we have r and p for our binomial random set. Again, n is the size of our grid, n times n, and p is the probability that if we ask a specific point, are you in our random subset or not? Then with probability P, it says, yes, I am. Or with probability 1 minus P, it says no. And the good thing is that, like I've already said, these two point sets basically relate to each other. If P is chosen in this case, M over N squared, then we expect this binomial random point set to somehow to behave like this in some sense. And there's a specific notion of monotone properties. So if we're interested in a property of our random subset that is not destroyed by adding a point, for example. So if we have a dominating set and we add a point to our dominating set, of course, it will still be dominated. So this is what we would call a monotone increasing property, this domination property. Or if we think about the point sets in general position, if you have a point set without collinear triples and you delete the point, then it will still be a point set without collinear triple, right? So this would be a monotone decreasing property of a point set. And when we have these monotone properties, then there's actually a very, very nice, strong relation between these two subset models. Namely that we can bound the probability that R and M has this property by 2 times the probability that the binomial random point set has this property. So if we can show that this goes to 0, then this of course also goes to 0. And dealing with these R and Ps, this binomial random point sets, is way, way easier. Because since we choose the points independently to be in our set, we only basically have to consider local information about this point set. Whereas here in this R and M random subset, we really have to understand the full set in some sense. So this is way easier to deal with. And the general idea would be now that you would try to prove this heuristic from this side here, from the binomial random point set. And so just to let you know, I tried to do this classic idea more or less with the no-three line problem. And even in this random point set, the dependencies are way, 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 way too high, like by a factor of log n or something. So you get really nothing, at least I didn't get anything out of it. But you might be smarter and more knowledgeable or something in this field. However, for the dominating sets, this actually works. So let me maybe explain briefly what the idea is when we do this probabilistic idea. So let's say we have S, our random subset, and or any subset of our grid. Then we know that S is dominating if and only if for every square in our board we have a dominating pair. So for this square here, for example, we have these 2 pawns that we call dominating pairs that would dominate this square, right? And now the idea is basically to show that there's a random subset where every square on the field has a dominating pair. So we start with taking R and K, where K is, again, like in the heuristic of Guy and Kelly, we only determine it at the very end when we want something to converge to 0. So we take a uniform random subset, and then we move on to the binomial random subset because it's easier to deal with. We have this inequality. And then so as soon as we have this binomial random point sets, the computations, I won't go into the details of the computations because you can actually watch another online talk from the graduate online combinatorics seminar where I talk more about this proof and I talk more about a setting on the discrete torus where there's more details, but basically we do the computations with this binomial random point set, and we show that the probability that there exists a square without a dominating pair is strictly smaller than 1. And if this is true, then we know, okay, there's a realization where there's no square that is without dominating pair, and that's it. That is the proof. And I tried this for the n times n chessboard, and it does give you non-trivial upper bounds, like I think 1.4n or something like this, but we already have this upper bound n from our specific construction that is not even that good. So on the normal chessboards, this is not very powerful, this heuristic. but on the torus it is. So if you've ever played torus chess, cool. I never did, but well, people somehow like to think about this. And also in mathematics, like the discrete torus, it's really just the integers modulo n times the integers modulo n. And there's lots of problems in this field, also for higher dimensional toruses. Like, for example, think about the CAPSET problem that really deals with lines on higher dimensional toruses and whatever. So there's big important problems on this discrete tori, and it's actually very natural to extend this problem to the torus. Also, the no 3-in-line problem on the discrete torus, if n is prime, is fully solved. We know you can place at most n+1 points on the discrete torus such that there's no collinear triples. And also, if n is not prime, then there's also some very strong results on the no 3-in-line problem, and it's partially solved. So there you have a lot of structure, and if you think about it, so this is basically a group, and the line would be a maximal, and the line on the torus is actually a coset of a maximal cyclic subgroup of this group. So you also have a lot of algebraic structure, I would say, in this setting, and you don't just have to rely on really geometry in that sense. Right. So in a discrete torus with this idea, we can prove if n is prime that the domination number is bounded from above by square root n log n, and from below by n square root n. And now you might think, what? But we already proved that the lower bound is n to the 2/3, but only in the plane. And this is because on the discrete torus, every line really dominates endpoints. And there we can only, by this counting argument, we can only prove the n to the 1/2 lower bound. And we can see, okay, the window here for the domination number is relatively small. So we only have a factor of square root log n here more. And so here in this setting, this heuristic is actually very, very powerful. Now you wonder why we need n to be prime. Well, n to be prime is because if n is prime and you have 2 points on your discrete torus, it really just defines one line. This is the magic about n being prime. If n is not prime, then 2 points can intersect with more than one line. They can intersect with 3, 4, 10 lines, depending on the prime factorization of your n. And we can actually prove that if n is a composite number and p is some prime factor, that the domination number of the torus then is bounded from above by 2 times p plus 2. And if n is divisible by 2 or 3, then this number is actually 4. We know that. So it's a very interesting problem here, because on the n times n chessboard, we do not know whether the domination number is monotone, so whether it really increases as n grows large, but but we assume it is the case. But here on the torus, it's really, okay, you have a prime number and the domination number will be at least square root n. But then the next number will be an even number and the domination number will be 4. And then you might have a prime twin and the domination number is again at least n squared. But then the next number will be again even and it will be 4. And the next number will maybe be divisible by 3. And it will again be 4. So it's somehow like an indicator function of your number being prime somehow. So it's very closely connected to the nature of your integer. And yeah, so I think actually this bound here in general can be improved. So I think this is like the easiest open question if you want to think about this torus problem, to improve this upper bound, because this is a specific construction and it doesn't use much magic. There's very much magic that one could use for these constructions if you're into this setting. Right. For the independent domination number, we do not know much about the discrete torus. We just know it's bounded by the numbers that we have from the no 3-in-line problem and from above again here by n to the 1/2. So maybe let's sum this up, what we know, and then maybe you have questions on what we do not know. So on the usual n times n chessboard, we know the domination number and also the independent domination number is bounded from below by n to the 2/3 and from above by n if n is even and n plus 1 is odd. And on this weird torus setting, we know that the numbers are actually way lower. So if n is prime, then the domination number is bounded from below by square root n and from above by square root n log n. And if n is a composite number, we have an upper bound of 2 times p plus 2, where p is some prime factor. And if you're interested in more, like I actually didn't even mention all open problems and all variants that we considered, but there's a paper on the archive that you can go through and maybe you feel inspired. Thanks.
Okay, can we please thank Eva for a brilliant talk? And if you have questions, please throw them in the Q&A or in the chat, and we'll hopefully Eva can answer them. In the meantime, while people maybe are typing them out, I had one. Is there a variant where you're allowed to put pawns outside of the board, and does this in any way relate to the solutions that you might be able to get in the torus?
Yes, there is a variant where we allow pawns to be outside of the board, and this number can actually be smaller. For example, if you have wait, what was it? A 2 times 2 grid. I mean, it's a ridiculous example, 2 times 2. But if you place a pawn at the left corner and then you place a pawn right above the grid and one right below the grid, then you only need 3 pawns to dominate the 4 squares. So also for n is 7, I think we have a better solution if you allow pawns to be outside of this thing, but it does not really relate to the torus, even though I agree it would make sense, because of course the torus is just a projection of random points that you can place everywhere.
Cool. And I had another, I don't know, variant in mind. Maybe this shows that I'm more of a problem maker than a problem solver, but is there perhaps an adversarial version of this game where someone can place a bunch of black pawns down on the board, and then you have to figure out how many white pawns you'll need to always dominate those black pawns?
Interesting question. No, we only had this game variant where you're not allowed to create collinear triples. But yeah, I also thought about this, trying to dominate the black pawns. And so far, I do not have any like real good results on that. But that would definitely also be a thing that in a break of a conference or something, one would like to try.
Yeah, I feel like it would be interesting to figure out what some naive strategies for black would be there. Which parts of the board would be good places to start with. We have a question from Jody. How do we even know an independent dominating set even exists for large n on the normal board?
Oh, you just place pawns greedily, basically. As long as there's a square that is not dominated yet, you can place a pawn there, and you will know that there's no collinear triple. Otherwise, there would have been a. But it's funny because I get this question at every talk. Does it even exist? It's a real math question somehow. But yeah, the answer is yes. You can greedily, I mean, not very efficiently, but greedily you can create these independent dominating sets.
That's a very simple proof by contradiction once you see that argument. Nice. Did we have any other questions? No, it doesn't look like it. My brain's telling me that I did have one more question, but it's escaping me right now. No, okay, a couple more have just jumped in. Brilliant. Okay, we got one from Angus, who asked, what do you think the real value of dn is?
Yeah, it's an interesting question. I actually like to believe that it's sublinear. I mean, it's.
Is there an intuition for that, or is that just something that you would really like to be true?
I would like that to be true somehow.
Cool.
But no, I have no idea what the real value for Tn is really, because we don't have large numbers.
Okay. And we have a question from Jeremy, who asks, do you have any intuition about geometric domination with other types of pieces?
What do you mean by other types of pieces? Like, you mean where we restrict the lines somehow?
Yeah, I imagine more like with the traditional pieces, you're only allowed lines of certain directions, right? Perhaps, yeah, but in the typical domination, you're all right, Jeremy's joined, so maybe he can fill in.
Sorry, is this like how we said we couldn't? Sorry, I'm getting feedback. Okay. With the pawns, how if you did it in the normal way, it didn't make too much sense. So then you added the fact if you had two pawns on a line, they'd dominate along that line as well. So if you did a two queens, adding that extra form of domination.
Ah, okay. Interesting question. Good question. No, I haven't thought about this. No.
Because
but that would be like something like a mix of the two dominations.
Yeah, because it wouldn't be like a graph anymore, like with the pawns, but then you still have that type of graph domination as well.
Ah, okay. No, I have no idea. But then we certainly have the classic bounds from the graphs. But
yeah,
we would probably need less. We would probably need less pieces here. But yeah, interesting question.
Okay, it doesn't look like we got any more questions in the chat, so we'll thank our speaker one more time.
Thanks for inviting me, and have a nice Friday night.
Thanks, we'll do.